Today is day 18 of Unit 5. We started today with this warm-up. There was a handout provided for the warm-up, but if you don't have that, I think I attached it to Schoology. But if you don't have that, you can just copy down the equation and then use the equation to find rational root theorem and Descartes' rule of signs. So take a moment, pause the video, try that, do rational root theorem and Descartes' rule of signs, and find all of the possible rational roots and the number of positive and negative roots. So let's go ahead and do that now. So first, why don't we do Descartes? So I'm going to count sign changes here. So I see positive, whoops, thought I already got a pen, but apparently not. So I see positive to negative. I see positive to negative, that's 1. I see negative to positive, that's 2. I see positive to negative. Positive to negative is 1, negative to positive is 2, positive to negative is 3, and negative to negative, so just 3. So we know that that means 3 or 1 positive root. So then we're going to find f of negative x, which would be negative x to the 4th power, which is x to the 4th, minus negative x cubed. Well, negative x, the quantity cubed, gives me negative x cubed. Negative x cubed times negative 1 is plus x cubed. Negative x, the quantity squared, gives me positive x squared times 2 is positive 2x squared. Negative x times negative 4 is plus 4x, and then minus 8's on the end. So checking number of sign changes, I see positive to positive, 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 positive to positive, positive to negative. That's 1. So there is 1 negative root, and either 3 or 1 positive root. So that's Descartes. Now, rational root theorem, the p's over the q's. So factors of the constant are factors of 8 over the factors of the leading coefficient, which are just 1. So we have plus or minus 1, 2, 4, 8 over plus or minus 1, which gives me just plus or minus 1, 2, 4, or 8. So that's what our list of possible rational roots are. And we have our, from Descartes, our number of positive roots and negative roots. So that takes care of the warm-up. So then for class, what we did was just continue on with this problem. So I need to figure out where all of the roots are so that I can graph this polynomial. So the first thing I'm going to do, step 1 of graphing polynomials, is actually you want to check to make sure that the original equation is not factorable. And if it is factorable, you're going to factor it. This one is not factorable though. Okay, but some of these polynomials, they'll be factorable from the very beginning. So if you can factor, you want to go ahead and do that because that's going to be easier if you just factor. This one unfortunately doesn't factor. So the second step of graphing polynomials after you try to factor is to do Descartes, which we did here, and rational root theorem. Okay, and I just had students write down the steps in their notes. So step 1, factor if you can. Step 2, Descartes' rational root theorem. We also can find the end behavior. We did that before we left for break. We remember positive and even degree means that it's going to have an up end behavior. So we can just include that in step 2 is to find the end behavior. So step 3, what we're going to do next is we're going to make a table. And the table that we make is going to include always, no matter what the polynomial equation is always going to include -1, 0, and 1. We're using those values because they will hopefully help us to one of two things: either find some roots, like one of those 3 or some of those 3 values will be roots, or if they're not roots, they might be able to help us know where some roots are located. So I'm going to get the y values by obviously just substituting into the original equation. So let me do that now. So I'm putting -1 in, so -1 to the 4th power gives me 1. And then I'm subtracting, I'm taking -1 to the 3rd power, which is -1, but then it's a negative in front of that, so that's +1. And then I have +2 times -1 is being squared. -1 squared is 1. 1 times 2 is 2. And then I have -4 times -1, which is +4. And then I have a -8 on the end. So let's simplify that. 1 plus 1 is 2. 2 plus 2 is 4. 4 plus 4 is 8. And 8 minus 8 is 0. Yay, we like that because we just discovered a root. Okay, so that's good. So we're going to just do the rest of the table, though, see if we can find any others. So 0 to the 4th minus 0 cubed plus 2 times 0 squared minus 4 times 0 minus 8 gives us -8. That one's nice and easy. So on your warm-up there, it asks for the y-intercept. You can go ahead and list 0, -8 is the y-intercept. It also is an important point in our table. Now putting 1 in. 1 to the 4th is 1. 1 cubed is 1, so 1 minus 1. 1 squared is 1 times 2 is 2. -4 times 1 is -4. And last, -8. So 1 minus 1 is 0, plus 2 is 2. 2 minus 4 is -2, and -2 minus 8 is -10. So we're not getting a root there. So what we did notice here is this table allowed us to realize that we have a root at -1. So if you recall, before break, we did some similar problems with polynomials where I gave you the first root, and then from there you found all of the other roots. And if you recall, what you did was you used the root that I gave you and you used it in synthetic division. Well, this is kind of similar at this point because even though I didn't give you a root, we just found that -1 is a root. So it's like we're starting the problem where we were before earlier in the unit. So what I'm going to do is I'm going to run through synthetic division using -1. And because I know it's a root, I'm expecting to get a 0 remainder when I finish. So let's run through synthetic, keeping in mind that the equation, if there's any missing terms, then we want to fill in zeros. So I don't think I'm missing any terms here, but we would fill in zeros if we were. So 1, -1, +2, -4, and -8. Bringing the 1 down, multiply -1, add -2, multiply +2, add +4, 4 times -1, -4, add -8, multiply +8, and 0 is the remainder. So we just confirmed that x equals -1 is a solution, is a root. And now keep in mind what we did next when we did this earlier in the unit. If I gave you the first root and you ran through synthetic division and confirmed that that was a root, remember what we did next was we rewrote this new equation, or the simplified equation, by writing the equation of the polynomial that's 1 degree less. So our original was to the 4th power, which means this is the coefficient for the cubic. So this is 1x cubed minus 2x squared plus 4x minus 8. And we're going to set that equal to 0 because we're looking for the roots. So I see 4 terms, and I'm going to check to see if this factors by grouping. It may not. We have to check it. Sometimes it will, sometimes it won't. So let's see if this one actually does factor. So x squared would be the GCF, x minus 2. Copy the x minus 2. Yes, it's looking pretty good. +4 multiplied by x minus 2 gives us 4x minus 8. So that product equals 0. So looking at the two groups, we see GCF is x minus 2. We're left with x squared plus 4. And that product equals 0. So we see a solution here, x equals 2. And setting x squared plus 4 equal to 0. Hopefully you're thinking square roots technique. That's what I'm thinking. So x squared equals -4. Square root, absolute value of x on the left, 2i on the right. So x equals plus or minus 2i. Those are the two solutions, or the two complex roots. So let's check here. It was degree 4. We have 2 complex and 1 positive real and 1 negative real. So that makes a total of 4. So we have all of the roots. And not only that, but we can check with Descartes here. I have one positive and one negative real root. And Descartes said one negative, which we got, and either one or three positives. And we did find that there was only one positive root. So we know we have done everything correctly. Now, just be careful when we're using Descartes to help us. This is only telling us about the real roots. It's not telling us about the complex. So you don't want to look at the positive and negative complex and try to fill them in with Descartes. Descartes is only talking about the real roots. So we do have one positive real and we do have one negative real root, which matches up with what Descartes told us. Okay, so I am going to graph what I know now, but before I do that, I just want to mention one thing, and I talked about this in class today. They're not always going to be factorable here at this step. So I tried to factor and we lucked out and this one did factor. But let's say that we tried to factor this and it didn't factor. Let's talk about what we would do next. So what I would do next is I would go back up and I would look at my list of possible rational roots, and I would also look at Descartes. Well, we just found one real negative root, and we know from Descartes that there only is one negative real root. So when I'm trying more values, and when I say I'm trying more values, I'm saying I would run through synthetic division a second time using these numbers, 1, -2, 4, -8, and I would run through synthetic division a second time. But when I do that, when I try numbers from my list here in synthetic division, I'm not going to bother trying any of the negatives. And again, why that is because Descartes told us there's only one negative root, real root, and we already got one negative real root. So I don't care about -1, -2, -4, -8. I'm going to instead try with synthetic division +1 or +2 or +4 or +8. And I would keep trying those values until I got a zero remainder. And I would eventually see if I tried 1, I wouldn't get a zero remainder. So then I would try 2 and I would get a zero remainder. And I know that because we know the ultimate answer is x equals 2. But I didn't even need to do that because I was able to factor this. But keep in mind, sometimes they're going to be more difficult than this one, and you're not going to be able to factor that. So you are going to have to run through synthetic division again using these numbers from the list of possible rational roots. And again, I've narrowed this list down a little bit because Descartes tells me there's only one negative root, and we already found it. So we're going to try positive numbers from this list. But now that we have all the information we need, we're going to graph. So I'm going to plot the y-intercept. I'm going to plot the roots, so -1 and +2. And I know that earlier in the unit we did sketches, and so we said that the two complex roots meant that there was this extra little U shape somewhere. But that was when we were doing sketches. Now we're doing more specific, more accurate graphs. So I don't want you to include that extra little U shape to account for the complex roots because you don't know where to put it. You don't know if it's on this side of the graph or on this side of the graph. You don't know if it's below the x-axis or above. So we're not going to include that U shape. So all we're going to graph is what we know for certain. When you reach calculus, you'll learn how to figure out exactly where to put that U shape. But for now, we're just going to graph through at 2 and pointing up, because the end behavior is up, through at -1 and pointing up, and then touching that, oops, I went too far there, touching that y-intercept. So it almost looks like a parabola. Don't disregard this down here. It almost looks like a parabola there and it has roots at 2 and -1 and a y-intercept at 0, -8. But we know it's not a parabola because it's a fourth degree polynomial, but it does look like a parabola. And again, for now, that's how we're going to graph it. Later in calculus, you'll learn where to put that U shape. Could be over here on the right of the graph, could be over here on the left of the graph. There would be an additional loop or U shape, but we're not going to include that because we don't know exactly where to put it at this point. Okay, so that takes care of that problem. The next thing we did in class was we started this problem. We did not finish it, so I'm only going to go to about where we stopped in class today. But this is worksheet number 5 in Unit 5, problem number 4. So we started running through the steps that I gave you earlier, and that is first we check to see if this factors. It does not. So then we move to step 2, which is Descartes and rational root theorem and end behavior. The end behavior, I see it's even degree and positive. So again, this one's going to be up, up. Might as well get the y-intercept a while. 0, plugging that in, I see is 36. So let's go ahead and do Descartes and rational root theorem. So positive to negative, that's 1. Negative to negative, no. Negative to positive, yes, that's 2. Positive to positive, no. So that means 2 or 0 positive roots. Let's do f of negative x. So 6 times negative x, the quantity to the 4th, is positive x to the 4th, times 6 is 6x to the 4th. Inputting here negative x, negative, and x, and cubing it is negative x cubed times negative 13 is positive 13x cubed. Inputting negative x and squaring it gives me positive x squared times negative 68 gives me negative 68x squared. Inputting negative x times 87 gives me negative 87x, and plus 36 on the end. So checking sign changes. Positive to positive, positive to negative is 1. Negative to negative, negative to positive is 2. So that tells us there are 2 or 0 negative roots. Okay. Next, rational root theorem. So we're looking at the p's over the q's, which means the factors of 36 divided by the factors of 6. So we're getting plus or minus. We know 1 and 2 and 3 and 4 and 6 and 9 and 12 and 18 and 36 over plus or minus 1, 2, 3, and 6 gives us plus or minus all of those on the original list in the numerator 1, 2, 3, 4, 6, 9, 12, 18, and 36, because those are all over 1. If I put those over 2, I'm getting 1/2. 2 halves is already on our list. 3 halves. 4 halves is already on our list. 6 halves is already on our list. 9 halves. 12 halves already on the list. 18 halves already on our list. And 36 halves is already on our list. So moving on to thirds. 1/3. 2/3. 3/3 is already on the list. 4/3. 6/3 already on the list. 9/3 already on the list. 12/3 already on the list. 18/3 already on the list, and 36/3 is already on the list. Moving on to sixth. 1/6. 2/6 is 1/3 already on our list. 3/6 is 1/2, that's already on our list. 4/6 is 2/3, that's already on our list. 6/6 is 1 already on our list. 9/6 is 3 halves, that's already on our list. 12/6 is 2, 18/6 is 3, and 36/6 is 6 already on our list. So we can end our parentheses. So plus minus all of those numbers, that's our P over Q. Okay. So we have quite a long list this time. So now I'm ready for a So I'm going to go ahead and use -1, 0, and 1. Substituting -1 in -1 to the 4th is 1 times 6 is 6. -1 cubed is -1. -1 times 13 is 13. -1 squared is +1. +1 times -68 is -68. -1 times 87 is -87. And +36 on the end. So if I combine these, I believe I am getting -100. Next, putting 0 in, we already said that's 36. Next, let's substitute 1 in. So 1 to the 4th is 1 times 6 is 6. 1 cubed is 1 times -13 minus 13. -68 times 1 squared is 1, so -68 plus 87 and plus 36. So let's see here. I don't have this answer memorized. So 6 minus 13 is -7. -7 minus 68 gives me -75. -75 plus 87 gives me 12. Yep. And 12 plus 36 gives me 48. Okay, so we have -100, +36, and +48. None of those are 0. Okay, but don't fret, because we do still know some information. We do know that this output was negative and this output was positive. So I talked briefly about this in class. If I were to sketch that, just do a real quick sketch here. -1, -100 is way down here. And 0.36, it is way up here. And in order for me to go from that point to that point, the graph has to cross the x-axis. So if it crossed the x-axis, then that means there's a root there. So we do have some information from doing this table. We weren't lucky this time and we didn't get a root. We didn't get a 0 here for the y, but we do know that somewhere between this point and this point, the graph crossed the x-axis because the sign changed. It went from a negative to a positive. Then it continues on being positive, 36 to 48. So it didn't cross the x-axis again between 0 and 1, but it did cross the x-axis somewhere between -1 and 0. So what I'm going to do is I'm going to check x values that are between 0 and -1. And now I'm not just checking any old random x values between 0 and -1 because there's a ton. I'm checking using my list here. I'm checking x values between 0 and -1 that are on the list. So let's think about that. That means fractions, and not even all these fractions, just the negative fractions that are between 0 and -1. So that would be -1/2. That's not between 0 and -1. That's not between 0 and -1/3. -2/3. And that's not between, and -1/6. So the 4 values that I have to check using synthetic division are those 4 fractions. Again, I knew that it crossed the x-axis somewhere between this point and this point, which means those x values are 0 and -1, which means there's a root somewhere between 0 and -1. So I went to my list of the possible rational zeros, and I picked numbers from that list that are between 0 and -1. And then I'm going to run through synthetic division trying those 4. Now you're going to have to try a few. There's no real technique that I can tell you for one guess is better than another, but you're going to try a few. We started, just because we were running out of time, we started with -1/3, which ends up being the root. So I'll start with that one. You may not necessarily start with that. You're going to realize it's not the root when you get to the end of synthetic division and you don't have 0 as the remainder. So I'm going to write my coefficients here. I have 6, I have -13, I have -68, and I have 87 and 36. No missing terms, so no need for a 0. 6 comes down. Now, when you're doing 6 times -1/3, that's like 6 divided by -3. So we know that that's -2. Plus -13 is -15. -15 times -1/3 is -15 divided by -3, which is 5. Plus -68 gives me -2. negative 63. Negative 63 divided by negative 3 is positive 21. Plus 87 is 108. And 108 divided by negative 3, or times negative 1/3, is negative 36. So we have a zero remainder, which means we just confirmed that x is equal to negative 1/3. That is a root. Okay, so now what I'm going to do next is I would check to see if this polynomial factors. And I think when you try to factor it, it does not. Unfortunately, it does not factor. But it's worth giving it a shot. Now, that's about where we stopped in class, but I do want to mention one other thing before I stop the video, and that is not only did I just find one of the roots, and I still have to find the rest, and there's going to be 4 total because it's degree 4, but I want to remember all the information that I have. I want to look back to Descartes here, and I want to look specifically at the negative roots because that's what we just found. It says Descartes told us 2 or 0 negative roots. Well, we just found one that was negative. So that means 0 negative roots is out, which means we know that there's going to be 2 negative roots. Okay, we just found one, which means it can't be 0 negative roots, which means there has to be an additional negative root. So the next thing I would do after seeing if this factors and realizing it doesn't, the next thing we'll do, we'll start tomorrow in class, is we'll run through synthetic division again, using these numbers as our coefficients, and we'll run through this list only trying negatives. Okay, and that might take us a while because it's a big list, but we'll only try negatives because we do know for certain that there is one more additional negative root. And that's where we're going to stop for today. Your homework is to do all of worksheet 5. Sorry about that interruption, but your homework's going to be to do the rest of worksheet number 5, but you don't have to finish the problem we were just working on, number 4. Just try problems 1, 2, and 3. Get as far as you can. Try to get through all those steps, starting with Descartes' rational root, trying to factor, and then going from there to find all of the roots, and then graphing the polynomial. And then tomorrow we'll finish up problem number 4 on worksheet number 5.